Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Scattering Mechanism under the paper Characterization of Materials Part 1. After completing this module, students will be able to understand the scattering mechanism and the role of drift current in it, and also about the mobility in scattering mechanism. When electric field is applied across a semiconductor, it experiences an electrostatic force. This force accelerates the charge carriers of the semiconductor till they acquire a constant average velocity v. This saturation effect in the initial acceleration is reached because of the scattering of charge carriers with the impurities and the lattice vibrations. The mobility of the charge carriers is defined as the ratio of this average velocity and the applied electric field. At higher fields, the velocity of carriers saturates and they move with the saturation velocity. The scattering of carriers at the surface is more than the bulk of the material because of surface or interface scattering processes, thereby decreasing the mobility of the carriers. Inside the semiconductor crystal, the carriers move as a free particles and are not influenced by the atoms present in the crystal. The only impact of the crystal on the carriers is a change in their mass. A semiconductor contains both types of carriers, that is, electrons as well as holes. Electrons carry one negative unit of charge, while holes carry one positive unit of charge. So, when electric field is not applied, thermal energy causes these charge carriers to move in a random fashion. For non-relativistic electrons, the thermal energy associated with each degree of freedom is kT by 2. For bulk semiconductors, the room temperature thermal velocity of electrons is about 10 raised to power 7 centimeter per second. Until a collision event takes place, the carrier travels through the semiconductor in a particular direction. The defects, impurities, and lattice vibrations act as collision or scattering center for the charge carriers moving in the semiconductor. Out of these, the collisions from charged impurities and lattice vibrations or phonons dominate. On colliding with them, the charge carriers experience an abrupt change in their velocity as well as energy. Since the carriers undergo frequent collisions due to thermal energy, the motion of the carriers is semi-random. Even when electric field is applied across the semiconductor, the carrier movement can still be considered as semi-random, except the fact that the carriers are also accelerated between successive collisions. Although the random velocity of carriers is much larger than the average velocity parallel to the field, there is no net flow of carriers. Newton's law can be used to describe the carrier concentration, and force is equal to the product of applied field and charge on the carrier. At the same time of collision,
there is an abrupt variation in the velocity and energy of the carrier. However, after collision, the charge carriers again gets accelerated. Due to collisions, there is no average acceleration of carriers. However, they attain constant velocity quickly after collision. Because of collisions, a friction term appears in the equation of motion with a time constant t. The time constant can be described as the time during which the charge carrier loses its momentum, that is mv, and associated with the average carrier velocity of v. If the charge carrier has a constant acceleration between collisions, the time constant is equal to the time elapsed between two successive collisions events. Drift velocity. Now figure shown on the screen shows the motion of charge carrier drifting through a semiconductor under the influence of an applied field. Under the influence of electric field, the particle moves with a velocity of v. If the velocity of charge carriers traveling through the semiconductor is same, the current flowing through the semiconductor can be determined by dividing the total charge in the semiconductor by the time taken by the carriers to reach from one electrode to other electrode. That is, I equals to Q divided by TR, which is further equals to Q divided by L divided by V. Here T represents the transient time of a charge carrier moving with the velocity v over distance L. Thus, the current density within the semiconductor can be expressed as a function of either the charge density R or carrier density N, as J vector equals to Q divided by A into L whole into V vector equals to rho into V vector equals to Qn V vector.
So now, students, let us understand what is the mobility. While moving through the semiconductor, the particles do not travel in a straight line along the applied electric field. These particles experience several scattering events which continuously change their direction of motion in the semiconductor. This motion of charge carriers can even occur when any external field is not applied under the influence of room temperature thermal energy. In the case of a non-degenerate and non-relativistic electron gas, each electron has an associated k T by 2 thermal energy for each degree of freedom. The carriers move with a thermal velocity of about 10 raised to power 7 centimeter per second at room temperature, and this value is much larger than the usual drift velocity, that is on applying external fields of carriers in a semiconductor. So figure shown on the screen depicts the motion of a charge carriers both in the absence and presence of an applied electric field.
When there is no external field applied across the semiconductor, the charge carriers move randomly in the semiconductor while also frequently changing the direction of their motion. On application of an electric field, the carriers still move in random fashion. However, there exists an average effective movement of charge carriers in the direction of the applied field. Let us now consider the net movement of charge carriers without considering their random motion. As per Newton's law, the acceleration of charge carrier is directly proportional to the applied force as F equals to m into A vector equals to m into dv vector by dt. Here the force comprises the electrostatic force minus the force because of momentum loss at the time of collision divided by the average time between successive collisions. So F vector equals to Q into E vector minus M into V vector divided by tau. The average velocity of the charge carrier can be obtained by equating both the equations. So Q E vector equals to m into d vector v divided by dt plus m into v vector divided by tau. Let us now consider the steady state situation when the charge carrier has already been accelerated and has attained a constant average velocity. In this condition, the velocity of the carrier is proportional to the applied field, and the mobility of the charge carrier can be defined as the ratio of their velocity and the applied field as mu equals to v vector mod divided by e vector mod or equals to q tau divided by m. Thus, when the mass of the particle decreases and the time between successive collision events is larger, the mobility of the carrier increases. Thus, the drift current can be expressed in terms of the carrier mobility as J vector equals to Q into N into mu N into E vector. Thus, the discussion here considered the mass of the particle as m, which is the case for a free particle. However, while moving through a semiconductor, the charge carrier experiences the periodic potential of lattice atoms of the semiconductor. To incorporate this effect, the mass of the particle is taken as an effective mass m star instead of free particle mass as mu is equals to q tau divided by m star.
From this definition, mobility depends on drift velocity. An important factor deciding the drift velocity, excluding the effective mass, is scattering time, that is, the time for which a carrier is ballistically accelerated by an electric field before it gets scattered and changes its direction or energy. Two dominant scattering sources in semiconductors are ionized impurity scattering and acoustic phonon scattering, or known as the lattice scattering. Sometimes other sources of scattering might become significant, which include optical phonon scattering, neutral impurity scattering, defect scattering, and surface scattering. In each scattering, the energy is nearly conserved. These include scattering from acoustic phonons, impurities, piezoelectric scattering, etc. Acoustic phonon scattering involves the scattering of electrons from state k to k dash and involves the emission or absorption of phonons with a wave vector q. This process presumes that lattice vibration results little shift in energy bands. The potential for scattering process is produced from deviation in bands because of these small transitions of frozen lattice points.
So students, now let us study about the ionized impurity scattering. Semiconductor may be doped with donors or and acceptors, which generally get ionized and charged. When a charge carrier, either electron or hole, approaches these ionized impurities, it is deflected due to Coulombic forces. This process is called the ionized impurity scattering, and the degree of deflection varies with carrier speed and its closeness to the ion. With increasing the doping of a material, probability of collision between a carrier and ion increases, while the mean free time between two successive collisions decreases, resulting in lower mobility. When computing strength of such interactions because of long-range character of Coulombic potential, other impurities as well as free carriers significantly reduce the interaction range with carriers compared to the Coulombic interaction. When these scattering sources are close to the interface, problem becomes more complex because of the presence of disorders and crystal defects. Dangling bonds induce if defects create additional scatters in the form of charge trapping centers which cause free carriers to scatter. These charge trappers become charged after trapping a carrier and start interacting with other free carriers, thereby scattering them. When these scattered carriers are in interfacial inversion layer, reduced dimensionality of carriers makes the case different from bulk impurity scattering, since carriers only move in two dimensions. Furthermore, the interfacial roughness results in short-range scattering and limits the mobility of interfacial quasi-2D electrons. Lattice of phonon scattering. At temperatures greater than 0 Kelvin, atomic vibrations produce pressures or acoustic waves within the crystal. Often described as phonons, photons are also particles similar to electrons and thus may scatter with a charge carrier, either electron or hole. The concentration of phonons increases with an increase in temperature, which results in an increased electron scattering, thereby reducing the mobility. Next is the piezoelectric scattering. Piezoelectric effect occurs in the compound semiconductors because of their polar character. Though this effect is negative in most semiconductors, it creates local electric fields which deflect the charge carriers and scatter them. Piezoelectric scattering is more predominant at lower temperature when other scatterings are ineffective. Electric field arises due to the deformation of basic unit cells as strain appears in certain directions of the crystal lattice. Next is surface roughness scattering. It is a short-range scattering process caused by the interfacial disorder and checks the mobility of interfacial quasi 2D electrons. High-resolution TEM images have shown that interface is not sharp at atomic level and the actual position of the interfacial plane varies one or two atomic layers along the surface. These variations are random and cause fluctuation of the energy levels and thereby interfacial scattering.
Alloy scattering. It is the scattering produced by random positioned substitute atoms in the crystal sublattice of a compound or alloy semiconductor. This type of scattering only occurs in ternary or higher order alloys because their crystal structure often involves random positioning of some atoms in the crystal sublattice. Inelastic scattering. Inelastic scattering causes a significant amount of energy exchange. Like elastic phonon scattering, atomic vibrations causes energy band deformation. Optical phonons that cause inelastic scattering having energies in between 30 to 50 milli-electron volt, while the typical energies of acoustic phonon are less than 1 milli-electron volt. The carriers undergo considerable variations in energy during the scattering process.
Electron-electron scattering. According to Pauli exclusion principle, electrons may be regarded as non-interacting for densities around 10 raised to power 16 to 10 raised to power 17 per centimeter cube, or electric field up to 10 raised to power 3 volt per centimeter. If any of these properties attain values much more than these limits, electron-electron scattering dominates. Nonlinearity and wide range of Coulombic potential influencing these interactions adds further complexity to them.
So students, let us now summarize what we have learned in this module. So we have seen about the scattering mechanism. We have also learned about the drift current in scattering mechanism, and we also studied the role of mobility in scattering mechanism. Thank you.